we had the enumeration of the states using the quantum numbers of the ideal gas, the free particles. We started somewhat doing discussing the ensembles, what we mean by ensembles, and today we will be starting discussing the canonical ensemble. We will have different approaches. One of them will be what the ensemble theory tells us about this ensemble. But the ensemble theory, there's the Liouville theorem, which basically, okay, this is the, which basically states that the density of the, in phase space, the density of the ensemble is some conserved quantity. And then we went back to the microcanonical ensemble. We minimized the entropy. We will come back to this entropy point also in the canonical ensemble. And as another example, we also looked at the harmonic oscillator. And one of the things that we were trying to identify was, okay, on one hand, we have the classical picture where the microstates form a continuum. So if you ask the question, what is the number of microstates, that basically doesn't make any sense, because we have, in any region, you have infinitely many points. But we said that, okay, we don't really count the number of states, but we determine the area of the hypersurface allowed for our system, and that is a measure of the number of states. Well, quantum mechanics solves that problem, saying that in the phase space, in P and Q phase space, you cannot localize the state to a point. Any microstate basically occupies a finite volume. And the question was, what is that finite volume? What does that finite volume correspond to in classical physics? So that we can use it in classical physics, and it is basically 2 pi h bar for each degree of freedom, momentum, and coordinate. For each dimension, we have a 2 pi h bar. And we saw this both for the harmonic oscillator and also for the free particle. And basically, what we claim is if you sum over all microstates, we will always identify this as d3 and p, d3 and q, divided by 2 pi h bar to the power 3n. n being the number of particles, 3 is the dimension. So we will have this identification. Any questions up to here? Now, today we will start in the microcanonical ensemble. What we were looking at was, we were looking at states with definite energy, volume, the number of particles. They were fixed. They were not allowed to fluctuate. And then we said that all the microstates are equally probable. All the microstates available to our system. Now, from a realistic perspective, okay, it's kind of easy to fix the number of particles. You just put it in a closed container. We can prevent particle exchange. Volume, having constant volume, it can be done, at least for gases, easily. For other systems, it will be problematic. Well, you see, if you want to keep the volume of a solid object constant, even if you change its temperature, that would require huge pressures, because with changing temperature, it will try to expand. If you want to keep the volume, you have to balance it by a huge pressure. Well, the energy is kind of the most difficult to keep fixed. Yes, you can say that, okay, we can just isolate it. We don't allow any energy exchange. But even in that case, there is a black body radiation as long as it has a finite temperature, as long as the container has a finite temperature, the environment has a finite temperature, there will always be some energy exchange. So a more realistic system would be to allow the energy to fluctuate. So we will look at a system which can exchange energy with the environment, but still we would like to have the average energy fixed. So that is what we would like to study. So we will be looking at a system where energy exchange with environment is possible, but average energy is fixed. So this is basically what brings us to the canonical ensemble. Now the system we have is, there's a heat reservoir at a given temperature T. That system is in equilibrium with itself. And there's this external system, the system that we are interested in. And of course, it can exchange energy with the heat reservoir. We don't allow the number to change. The volume will be fixed. And when the system reaches equilibrium with the environment, it has a temperature T. Now, the first question we will ask to ourselves is, of course, now the energy is not fixed. You see, in the canonical ensemble, we also ask this basically the same question. What is the probability that our system will be in one microstate? And we said that since all states are equally probable, the probability that it will be in one particular microstate will be 1 over the total number of microstates. So we basically looked at the total number of microstates and developed our microcanonical ensemble from that perspective. Now we ask the same question. What is P? Let me define P ER to be the probability that the system, this is my system, is in the microstate R that has energy ER. So this is the probability that we will be looking for. Once we have the probability, we can just go ahead and calculate all the averages, etc. So how do we write this probability? Okay, before that, I'm looking at a system that is not isolated, but I can consider another system. This is my whole system. This is isolated. And has total energy E0, let me call that E0. My whole system has some energy. It is fixed since the whole system is isolated. But now, since it's an isolated system with fixed energy, the number of particles, etc., I can use the microcanonical ensemble to describe the whole system. My system plus the reservoir. So now I can ask this question of this probability to my whole system. What is the probability that my subsystem will be in the microstate R, in one particular microstate? So what would you, how can we calculate this probability? How do you calculate the probability in general? If I ask you the probability of something.
Over the total number of microstates. The ways of getting this over the total number of microstates.
The ways in which the system is in microstate R divided by the total number of microstates of the whole system. So this is my probability. Now, what is the number of ways in which my system is in the microstate R? How can I calculate it? basically my whole system is made up of two parts. The ways in which the whole system, the ways in which my system is in that particular state will be 1, because that is the only state I want. I'm looking for the probability of my real system to be in one particular microstate. But of course, when I'm looking at the whole system can have many ways in which my particular system is in that one microstate, and that will be multiplied by, let me call that the reservoir having an energy E0 minus E of R, divided by omega of the whole system to be in the state E0. This is my P of E of R. The denominator is the number of ways in which my whole system can exist having the energy E0. The numerator is the number of ways in which the whole system can exist such that the system I'm interested in is in that one particular microstate. You see, P of E of R is not the probability that my system will have an energy ER. P of ER is the probability that my system will be in the microstate R. So any questions on how we write this?
I don't understand the factor 1. Sorry.
If you have two events, one event will be my system, the microstate of my system. The other event will be the microstate of the reservoir. And then I ask you the question, how many microstates can my system can be in such that my whole system plus the reservoir, can be in such that my system, the system I'm studying, is in the microstate, in that microstate, one microstate. So you just multiply the number of ways in which this can happen. I'm looking at one microstate of my subsystem, of my system. So that is one. That is this one over here. But when my system is in that particular microstate that I'm interested in, the reservoir can still be in all of these microstates. Why do I subtract ER? Because that ER is already in my system.
Okay.
The reservoir has an energy E0 minus E of R.
So just to be clear, if we were looking for multiple microstates, that's the factor that will change.
Yes, that would be.
Okay.
For example, if I would be asking the question, what is the probability that my system will have an energy ER, then instead of 1, I should put the number of microstates of my system that has an energy ER.
Okay.
I'm confused about the second part.
Which part?
There is E0 minus ER.
Yes.
So ER the energy of that state we want.
Yes.
But why there is a minus? It looks like
because the
the
reservoir.
whole energy minus that energy. So
Well, you see,
besides
I have my system plus the reservoir. My system has energy ER and the whole system has energy E0.
okay.
So the reservoir has energy E0 minus E of R.
Okay.
So this is the, you see, this is the energy of the reservoir only. And this is the, well, let me put a capital R over here. Number of microstates of the reservoir only.
So do we want 1 minus this number?
Why? Why should I want 1 minus this number?
Because this gives us the argument of the function regard.
So let me write it in this form. The number of microstates of the system times number of microstates of the reservoir divided by number of microstates of system plus the reservoir. This is what I'm writing. So number of microstates of the system, I'm not looking at the total number of microstates, I'm just looking at the number of microstates whose probability I am calculating. So that is why it is 1, because I'm looking for the probability that my system will be in one particular microstate. And this is, that's omega r is the number of microstates of the reservoir only for the energy E0 minus E of r. E of r is in my system, the remaining is in the reservoir, and that is E0 minus E of, yes.
If we say PER, and it's more like, and if that energy level has like different states.
As a degeneracy, yeah.
Indigenous, then that probability statement might not be true. Like maybe we should do PR.
Well, that is why I wrote this explicit definition here. That's the probability that the system is in the microstate R. But as a function, it only depends on ER, as we will see in a moment. It only depends on the energy of the system. Well, you see, if I were writing the statistical mechanics myself, I would have used that notation. But the general notation is P of E. Since it's already a fixed convention, I will stick with it.
In the denominator, shouldn't it be the subsystem plus reservoir?
Okay.
It should be subsystem, right? Because
No, you see, what I call the system is this one. This is my system. This is the reservoir. Since I'm only looking at that system, I'm still calling it the system, but I said that I can also consider my system plus the reservoir as my whole system. Of course, my system is now the subsystem of the whole system. But still, since I'm mainly interested in the system, this one over here, I will keep calling it the system plus the reservoir. Of course, my system exchanges energy with the environment. So ER, the microstate of my system will change, ER will change. Now the question is, what is the most probable system? Well, to calculate the most probable system, we can minimize, well, let's see. This is constant. So if I want to maximize P of ER, I can just try to maximize this function. As a function of ER. Now it will be a highly peaked function. So let's say instead of maximizing omega r directly, we can also maximize its logarithm. Because you see the number of microstates will be huge. And so taking the logarithm gives us a more reasonable number, so we can try to maximize this one. Or, I mean, even, let's forget about the maximization. P of ER is basically proportional to e to the power logarithm of omega r e minus ER. Because now I will be E of r, which the reservoir is huge, E of r is much, much less than E of 0. So I will make a Taylor expansion of the logarithm rather than omega itself. Well, this is equal to logarithm of omega r at E0 plus derivative of the logarithm of E of r as a function of energy, evaluated at energy is equal to E0, multiply by minus E of R, plus I have higher order corrections there. Well, this is again just a constant, independent of E of R. So this is equal to constant plus, well, remember from the canonical ensemble, logarithm of omega is nothing but the entropy of the system. S over K of the reservoir. But this derivative is nothing but 1 over the temperature of the reservoir. But in equilibrium, that's also the temperature of my system. The temperature of the whole system. Plus, of course, there are other terms. So P of E of R will be some constant times e to power minus E of R divided by KT. So basically, if you have a system that's in contact with a heat reservoir at the temperature T, the probability that at a given instant you will observe your particle to have the temperature, to be in the microstate R, that probability will be determined by E of R only, and it will be given by this number. Well, the sum of the probabilities should be 1. So the normalization should be here I'm summing over all the microstates of the system I'm studying, not without the reservoir.
Is that constant, last constant you wrote in multiplication?
This constant over here.
No, the one below that.
Here, this is multiplication.
Okay.
You see, that this constant in the expansion of the logarithm, since it's e to the power the logarithm, so it's e to the power constant minus E of R. Well, let me give some names. So let's say this is A. Well, this is some constant times e to power A minus E of R divided by KT. Well, this constant over here, you see, the probability is not just omega R. It's also divided by this, the total number of microstates of the combined system, the system plus the reservoir, which is also another constant. This A over here is this A over here, but that's also another constant. So this is just some other constant. Now this constant is determined by the total number of microstates of the reservoir and also this small a. But I don't need to calculate it from the total number of microstates from the reservoir. I can just use the fact that the total probability should be 1. And hence, I get this expression. Sum over R, P of R should be equal to 1. And now I can ask the question, what is the energy of the average energy of the system? Well, the average energy is sum over all the possible microstates of the system, the energy of that microstate times the probability of that microstate, which will be R, E of R, e to power minus. Let me call this sum Q. Divided by Q. U will be equal to e to power, well, let me call the beta 1 over KT. I will evaluate this, everything at beta is equal to 1 over KT. Now, if I take the derivative with respect to beta, it will bring down a factor minus ER. So let me also multiply with a minus sign and divide by Q. Well, what I did was this. I just took the 1 over Q factor out of the summation sign. I have a factor of ER multiplying the exponent. I just write that as the derivative of the exponent, because if I take the derivative with respect to beta, that will just bring down an ER. But derivative with respect to beta is independent of the summation over the microstate, so I can just take that out. So this is minus 1 over q del over del beta, sum over r e to the power minus beta e of r. Again, keep in mind that beta is 1 over kt. Well, this is now nothing but q. So the average energy of my system is minus 1 over q times the derivative with respect to beta of q, which is minus derivative with respect to beta of logarithm of q, keeping v and n constant. Where did I assume that I'm keeping v constant? I wrote it over here.
Change.
Change in entropy.
You see, here I haven't yet mentioned entropy. I don't know how to calculate entropy yet. You see, I'm just saying that this derivative over here is actually the derivative of logarithm of beta, keeping v and n constant. So where did I assume in this derivation? Starting here.
All systems isolated.
Well, we are looking at a system that is not isolated, because it's exchanging energy with the environment. It can have any energy, in principle. You had
You're
understand.
looking at a system that doesn't have a changing volume
Where did we assume that?
at the very top, not in the.
No, you see, I'm just asking you this derivation. Start from here.
So it must be
I mean, if you look at this, what I did was here I took the derivative with respect to beta, and then took the beta out of the summation, and then converted everything over here. So at some point, I did make the assumption that as I'm changing beta, I'm not changing the volume. At which step did I assume that? What does volume affect in this derivation? Which of these factors, starting from here, which of these factors or terms depend on the volume? Now the temperature is independent of volume.
Q, total number of microstates, Q.
So how does it depend on volume? If this is Q, where is the volume? Where does the volume appear here?
Okay.
It does appear there, that's why I'm asking. There is a place where in that definition V appears.
Yes.
Where?
It should be multiplied.
Why? You see, that is my definition. I can just define whatever I want. And that definition already depends on V, on the volume.
I think it appears at the del over del beta e to the minus beta er. It's basically del er, del t of the energy of something.
You are on the right track.
I think it's on the summation.
No,
The
summation
values
doesn't.
R can take.
Well, he is closer. Just remember the ideal gas problem we studied. What are the energy eigenvalues of a particle in a box?
Did we assume temperature to be constant?
Well, I'm taking the derivative with respect to temperature. So that derivative already assumes that there is some variation. The heat reservoir has a temperature.
So T depends on the volume.
No. Why should it? I can just adjust the temperature of my heat reservoir without changing the volume of anything. So what is the energy eigenvalues of an ideal gas in a volume, in a box? Energy of the ideal gas particles in a box were proportional to 1 over L squared, which is nothing but 1 over V to the 2/3. So energy eigenvalues, these ones, are actually functions of the volume. So that is already, you see, when I write this derivative over here, I'm saying that I should only take the derivative with respect to beta. I shouldn't change E of R as I'm changing beta. So as I change the temperature, I shouldn't change the volume so that ER will be constant. That is the assumption where I made. So this derivative is already at constant volume, at constant number of particles. I should change, well, what is the derivative? You just change your function slightly. You just change your argument slightly and look at how your function changes. So that derivative tells me that, okay, change beta slightly, but make sure that V and N do not change so that ER doesn't change. ER also depends on N.
So here again is
The energy of the microstate. The energy levels, they depend on the volume and the total number of particles. But here, I just want to take the derivative with respect to this factor beta. I don't want to take the derivative with respect to ER. Otherwise, this equality does not hold. Well, actually, I should take the derivative keeping all the ER constant. But in terms of the macro state, keeping all the ER constant basically means that I'm keeping the number of particles constant, I'm keeping the volume constant.
There was a question there that we equates to the entropy.
We will come to the entropy. You see, this is the energy is equal to minus the derivative with respect to beta of logarithm of Q. No. This derivative is at constant V and N. Of course, you are probably mentioning that we had du from thermodynamics, TdS minus PdV. Well, this doesn't help me right away. Now we still have the question, okay, this is fine, but what is logarithm of Q? How can we relate that to any thermodynamic quantity that we know? You see, our variable here, the variables we have are V, N, and T. Now this is my thermodynamic relation. Du is equal to TdS minus PdV. Well, if you like, let me also add the mu dN. Well, it has the entropy as my variable, so I would rather change that. I can write du minus Ts is equal to minus SdT minus PdV plus mu dN. So that this is what we call the free energy. In your book, the note, it uses A. Well, the energy of my system is the free energy plus T times S. The free energy minus T times S is the derivative of free energy with respect to temperature. Well, I'm not writing constant V and N, just keep in mind that V and N are constant. Well, let me write it at this step. I will just ignore it in the next steps. Well, let me try to write this. Well, you see, this is U. This is another expression of U I have, and that the expression of U I derived from our statistical arguments is the derivative of something. So let me see if I can change this expression U to a derivative of something else. So let me write it slightly different, in a slightly different form first. Let me take a T squared out, or minus T squared out. So that will give me 1 over T derivative of F with respect to T minus 1 over T squared of F. Well, 1 over T squared is nothing but the derivative with respect to T of 1 over T. So this is U is equal to minus T squared derivative with respect to T of F over T, which I can write as differential of F over T divided by minus dt over T squared, again keeping in mind that when I'm calculating these differentials I'm keeping N and V constant, which is differential of f over t divided by the differential of 1 over t, which is differential of beta f with respect to differential of beta, or the derivative of beta f with respect to beta. So u is derivative of beta f with respect to beta, and at the same time is minus the derivative of logarithm of q with respect to beta. Again, both derivatives are constant v and n. So we can identify minus the logarithm of q with beta f. Or logarithm of q is minus beta f, or whichever one you want. F is equal to minus kt logarithm of q. So now we related the logarithm of the partition function. Q is what we call the partition function. The logarithm of q just gives us the free energy if you multiply it with the temperature, minus the temperature. Well, let's also look at the pressure. You see, if this is the free energy, the pressure will be equal to minus the derivative of the free energy with respect to volume at constant temperature and the number of particles. This is minus the derivative with respect to volume. Well, free energy, we just said that it's minus kt times logarithm of q. Keep in mind that we are taking this derivative at constant temperature and the number of particles. Well, these minus signs will cancel. This is equal to k times t times 1 over q times the derivative of q with respect to volume at constant temperature and number of particles. Well, we know what q is. Sum over all states e to power minus beta E of r. Now we see, since we are keeping temperature constant, beta is constant. The only thing that depends on volume is E of r. So this is equal to kt, 1 over q, sum over r, minus beta, derivative of E of r with respect to volume, e to the power minus beta E of r. Well, beta is 1 over kt, so this cancels this one. So this is nothing but derivative of minus d E of r by dv, e to the power minus beta E of r divided by q, but this is nothing but the probability. Well, this is pressure, this is the probability that my system will be in the microstate r. Now let me use P of r, PR over there. So the pressure is nothing but average of minus the derivative of E of r with respect to V. Well, I made an assumption here though. I'm assuming that as I'm changing the volume, I'm assuming that the probabilities are also not changing. The P of r are constant, so I'm not allowing, if you look at it from a quantum mechanical perspective, I'm not allowing my system to jump from one state to the other state. So that is what we call the adiabatic process, a slow process. But that is also already what we did also in thermodynamics. So I'm changing the volume slowly. Well, this is basically how the energy of the microstate changes as I change the volume. That is the pressure of that for that microstate, and the pressure of the system is This basically states that the pressure of the system is mainly the average pressure of the microstates. And again, this identification basically follows from this identification over here. Although we identify the free energy with minus kT logarithm of Q by just looking at how we can express the energy, but this also tells us that that identification kind of is the correct one because it also reproduces the correct pressure. Let us also look at what is the average of logarithm of P of R.
Before we move on, could you repeat where you assumed the adiabatic process here? Because I missed it.
Well, you see, adiabatic in the sense that when I'm changing my microsystem, you see here, basically when I come over here, when I write this expression, that last term over there, I'm saying that PR do not change as I'm changing the volume. Well, logarithm of PR was e to power minus beta ER divided by Q. So this is equal to minus beta, the average of R, and minus logarithm of Q. Minus beta U minus, well, logarithm of Q, we just said that it is minus beta, the free energy. So this is equal to free energy minus U divided by KT. But remember, free energy was U minus TS. So the average of the logarithm of the probabilities is minus TS divided by KT. It's just minus S over K. So the entropy is nothing but minus the Boltzmann constant times the average of the logarithm of P of R. Well, this is what I had stated before, saying that this is just the definition of that general definition of entropy. Here, I didn't make that definition, I didn't make that identification a priori, but at the end of my computation, this is what I obtained as the expression of the entropy. This is minus KB times P of R logarithm of P of R.
Q'yu Z diye gösteriyorlar değil mi?
Sometimes it's Z, sometimes it's Q. Any questions? So this is just one derivation of these probabilities, one possible derivation. So what we did over here is we are looking at a system in contact with a heat reservoir. Rather than studying my system, I studied system plus the reservoir in the microcanonical ensemble. It's an isolated system, so I already know how to treat them, and we just derived all these results. Now, we can directly use the ensemble theory. Remember, the ensemble is, you have your system, you just make many copies of your system and study your system. You can talk about the density of the states in the phase space. You can do all, well, whatever you want. So the question we have now is, let's say, this is my system. This is my system. This is my system. I have n copies. And let's say, let me call n R to be the number of copies in the microstate R. I can pick up randomly. I can pick one randomly among all these copies. I can ask the question, what is the probability that that copy will be in the state, in the microstate R? This will be NR over N. So now I can ask you the question, what is the most probable value of NR in this ensemble? Now my ensemble will be given by these numbers. I can ask the question, what is the most probable or the average of course these numbers have constraints. Sum of NR is equal to the total number of copies in my ensemble. Furthermore, the average energy will be, well, let me divide by N over here, this is U. So I have these constraints. I have many copies. Now I will be trying to understand what is the most probable value of these numbers and what is the average of these NRs. It will turn out that they are equal. Well, we will derive both of them and explicitly show that they are equal. The most probable value is the average. But that is what we will do in the next hour. So any questions, except on this one? Any questions up to here, Your questions about the ensemble, we will discuss it next hour. So let's give a 10-minute break and then we will continue.
Bu son, üçüncü, bu da son soru. Şimdi siz geçen dersten son zaten bunu yaptınız. Periyodik olunca şurası değişiyor olmayınca. Yani
Yok şimdi.
bir çeyrek